Hello, my name is Amrei Oswald, and today I'm going to talk to you about Hopf actions of some quantum groups on path algebras. This is joint work with my advisor, Ryan Kinzer. So what we're going to do today is we're going to study quantum symmetries of path algebras within the framework of tensor algebras in finite tensor categories, as developed by Eddinghoff, Kinzer, and Walton in a 2019 paper. And our main results are going to establish equivalences between bimodule categories in the representation category of certain rank 1 quantum groups and subcategories of representations of explicitly given quivers with relations. So in other words, we're going to take the problem of classifying quantum symmetries on path algebras and translate it into a problem in the representation theory of finite dimensional algebras. So we'll start by defining a path algebra. We need a quiver, which is going to be a tuple where Q0 is a finite set of vertices. Q1 is going to be a finite set of arrows. And then you have these maps giving you the source and target of each arrow. So essentially, it's going to be a directed graph. You can have loops. You can have however many arrows between each vertex going in either direction. And then we can define a representation of a quiver by assigning a finite dimensional vector space to each vertex and a linear map to each arrow that goes between the vector space assigned to its target vertex and the vector space assigned to its source vertex. So once we have a quiver, we can define its path algebra, which is the associative K algebra that has bases consisting of all the paths in your quiver and multiplication given by concatenation of paths where that's possible. So for example, we have these arrows alpha and beta. The target of alpha is equal to the source of beta, and so these give a path alpha beta when we multiply them. But gamma and delta, their source and target don't line up correctly, so when we multiply those, we get 0. And another way we can see a path algebra is as a tensor algebra. So if we take KQ0, which is a subalgebra generated by all the paths of length 0 at each vertex, and we take KQ1, which is the subspace spanned by all the arrows in your quiver. KQ1 is a KQ0 bimodule, where the action of KQ0 on KQ1 is just multiplication. And so we can form the tensor algebra with base algebra KQ0 and generating bimodule KQ1, and that gives us our path algebra back. So now we'll look at parametrizing actions of UQB on path algebras. So UQB is going to be an example we use throughout this presentation. It's generated by the skew primitive generator X and a group-like generator G, which has an inverse. They satisfy these relations. And we're going to assume that all Hopf actions preserve the filtration of the path algebra by path length. So when I say action, I mean a filtered Hopf action. And so the following data is going to parameterize an action of UQB on a path algebra. And all Hopf actions of UQB on path algebras will have this form. What we need is a Hopf action of UQB on KQ0, a representation of the group generated by the group-like element on KQ1 that's compatible with its KQ0 bimodule structure. And we need a linear endomorphism sigma of KQ0 plus KQ1 that satisfies certain conditions. So let's look at a picture to see what all of this means. So we need an action of UQB on KQ0. So the group-like generator, it's just going to permute the vertices as shown by these dotted pink arrows. And then when X acts on a vertex, it's going to take the vertex to a linear combination of itself and G acting on that vertex. The scalars in that linear combination are these gammas that show up again. And then we had a representation of the group generated by G on KQ1 that's compatible with its KQ0 bimodule structure. So what that means is if I take a vector in this arrow space, an arrow space is the vector space spanned by all arrows between two specific vertices. So V here is an arrow space. If I take a vector in this arrow space and I act on it with G, that's going to take it to a vector in this arrow space here. And so you can see the source and target change in accordance with the G action on the vertices. So that's what that means. And then the last piece, the linear map sigma. So that's going to come up in the X action on a vector. So if I take a vector in V and I act on it by X, I'm going to get a linear combination of the vector and G acting on the vector. And then I'm going to get this last piece here that's given by sigma. And what sigma does is it takes a vector in V and it sends it into this purple space W, which has the same source, but the target is G acting on the original target. So two important things to note that'll come up later. The action of G creates isomorphic copies of arrow spaces, and the map sigma maps between isomorphism types of arrow spaces, because this W here is not necessarily isomorphic to V. We have similar parameterizations for UQSL2, and we also have conditions that are easily verifiable for when these actions factor through quotients. So we have conditions for when an action of UQB factors through a generalized Hopf algebra, and we have conditions for when an action of UQSL2 factors through the small quantum group. So now that we kind of know what a Hopf action of UQB on a path algebra looks like, a natural question to ask is, what are the minimal building blocks of a quantum symmetry like this? And to answer that question, we're going to turn to C-tensor algebras. So a quantum symmetry is going to be given by a Hopf action of a quantum group on an algebra A. And so a Hopf action, one way to think of it is that it's an H module structure on your algebra A, where your multiplication and unit map of your algebra are H module homomorphisms. And that's just another way of saying that your algebra is an object in the representation category of your Hopf algebra, and your multiplication and unit maps are morphisms in that category. And so when you have a tensor category, you can define the notion of an algebra in that category by taking triples of an object and a multiplication map and a unit map and requiring that they satisfy certain diagrams. You can define modules in a similar way. And so if you have a Hopf action of a Hopf algebra H on an algebra, that's the same thing as saying that the triple, the algebra, the multiplication map, and the unit map form an algebra in the representation category of the Hopf algebra. So a quantum symmetry on an algebra can be thought of as saying that the algebra is an algebra in the representation category of the quantum group. And you'll recall that our path algebras are tensor algebras. So we're going to turn to the work of Eddinghoff, Kinzer, and Walton, where they developed the notion of a C-tensor algebra in a finite tensor category, where your base algebra is an algebra in that category, and your generating bimodule is a bimodule in that category. And so our question was, can we classify the minimal building blocks of Hopf actions of UQB on path algebras? So in Eddinghoff, Kinzer, and Walton, they defined this notion of a minimal faithful C-tensor algebra, which is a C-tensor algebra where your generating bimodule is indecomposable and no two-sided ideal of your base algebra acts by zero on your generating bimodule. And these are the building blocks of C-tensor algebras in the sense that all C-tensor algebras are direct sums of these, and these are the smallest pieces that you can get. And so what we want to do now is we want to realize our path algebras as tensor algebras in RepUQB. And we already have a notion of what a minimal piece might look like, because we saw in our example earlier that if we just have an arrow and we want to think about a Hopf action of UQB on that arrow, we need at least the g-orbit of its source vertex and the g-orbit of its target vertex. And so we're going to kind of keep that in mind as we construct these bimodules. So we're going to let S sub m be a path algebra of a quiver with m vertices and no arrows. So a set of m vertices like this. And we're going to give S sub m a g action so that all the vertices are in the same orbit, just like in our example. And then we're going to fix a UQB action extending this g action on S sub m. So now S sub m is an algebra in RepUQB. And we are interested in RepUQB tensor algebras where our base algebra is a direct sum S sub m plus S sub n. So two sets of m vertices and n vertices. And our generating bimodule is an SM-SN bimodule, which means some configuration of arrows between m and n. So this tensor algebra is faithful by construction. So now what we're interested in is classifying the indecomposable bimodules in the category of SM-SN bimodules in RepUQB. So we're going to construct a functor between that category and a category of representations of a certain finite dimensional algebra. And so you'll recall that we have these arrow spaces between vertices. And when G acts on those arrow spaces, it creates an isomorphic copy of the arrow space. And we can keep applying G until we loop back around. And we loop back around once we've applied G, least common multiple of M and N times. And so that means that if we act by G to the power L on this arrow space, we're going to land back in it. So this arrow space is a representation of the subgroup generated by G to the power L. And so what we're going to do is we're going to let this vertex here represent an isomorphism type of an arrow space. And then this loop is going to come from the nilpotent part of that representation of the group generated by G to the L. And then the last piece is that sigma, remember, maps between isomorphism types of arrow spaces. And so that's where these arrows A going between vertices come from. Technically, these vertices are like eigenspaces of isomorphism types of arrow spaces, but I don't want to get into all of that, so don't worry about it. So our formal definition of our quiver is that it has this vertex set here, and then the connected components are this infinite thing that we constructed earlier, if Q is not a root of unity, and this loop if Q is a root of unity. So if Q is a root of unity, we get this arrow going back around, and we're going to let gamma be the quotient of the path algebra of this quiver by all relations of the form BA equals Q to the LAB, where A and B indicate arrows as makes sense. And so then our result is the category of SM-SN bimodules in rep EQB is equivalent to the category of finite dimensional representations of gamma that are nilpotent on loops. And so gamma, the algebra, has what's called wild representation type, which means that classifying the indecomposable representations of gamma is at least as complicated as classifying any pair of square matrices up to simultaneous similarity. And so what that tells us is that classifying the indecomposable bimodules is also that complicated. And so it's not really feasible to do that classification. And then we have similar results for UQSL2 and generalized Taft algebras and the small quantum group. So I'm going to show you the quivers for those. So we'll start with Taft algebras. So we want Q to be a root of unity. And then the generalized Taft algebra is going to be this quotient of EQB here. And if R equals N, you're going to end up getting your regular Taft algebra back. And so we're going to end up with a finite number of connected components that are these loops here. The loops on the vertices are going to vanish. And we're going to have this relation where when we go around k times, that's equal to a constant. And so these are Nakayama algebras. They have finite representation type. And so that means that there's a finite number of indecomposable representations. And so classifying the bimodules is very doable in this case. UQSL2, we're going to restrict ourselves to the case when Q is a primitive Rth root of unity. And so UQSL2 has these Borel subalgebras that are isomorphic to UQ squared B and UQ to the minus 2B. And so what we get is we get two copies of those sets of loops that we had earlier, and they're going to run perpendicular to each other in a grid like this. And so this quiver is wild. It has wild representation type. And so again, classifying the indecomposable bimodules is not feasible in this case. And then the last piece is the small quantum group, which is this Hopf quotient right here. In that case, that grid of loops ends up collapsing down to these parallel sets of arrows. And we just have this one connected component. And we are not sure what the representation type of this quiver is. So if you happen to know, please let us know. And that's everything that I have for you today. Thank you for listening. Thank you to the organizers for giving me this opportunity. If you have any questions, let me know in the comments.